Hello guys. Today I'll be explaining you our paper, our CVPR accepted paper, DSCA, Dynamic Subspace Concept Alignment for Lifelong VLM Editing. So this paper is essentially aimed towards solving the problem of catastrophic forgetting, which is a very prevalent problem when we try to teach new concepts to LLM and VLMs. And it is most prominent in cases of VLMs. So let's first try to have our intuition, like why this is a problem in VLMs. So in VLMs, we have two modalities. While training, you show it the image and the caption. The model learns across its massive data set. The model learns how to relate the image tokens to the text tokens. So at the end of the pre-training, it learns a very fragile connection between image tokens and text tokens, and it's very specific. For example, if after a VLM is trained, let's say we have taught it how a car looks like. Now we want to edit its knowledge to show like how a truck looks like. We have a data set where we have different angle shots of Cybertruck, and their captions are, this is a Cybertruck shot from back and from front, like this. So when it is an observed phenomenon, like once the model has been fine-tuned on this new data set, what will happen? Then again, after fine-tuning, if we ask what is this, the same question, earlier it was answering correctly, it is a car. Then it may answer, no, this is a truck. It is happening because while fine-tuning, we are showing the model which looks something like a car, but has truck in its textual description. So this somehow alters the thin manifold which the speaking in a strict mathematical sense, it alters the thin manifold which the model has learned in its high dimensional knowledge representation. It alters that. The best way to visualize it is like picking a piece of cloth right from one point. If you pick the piece of cloth right from one point, then the surrounding points are also affected, right? They are stretched, their position is moved. So while teaching the model one single thing, it alters what it had learned, the connection it had learned, the connection between the image and text tokens it has learned among unrelated concepts as well. That's why the name catastrophic forgetting. It's a widely observed phenomena in knowledge editing paradigm. So we are trying to propose a solution for that. So we'll start with understanding this image which you have drawn. It's a you see this is the initial concept space. Uh, you can imagine this ellipse shows the parts of the model brain the, which relate to the concept of cat, and all these points are the points which are triggered when the model sees cat. It's a very hand-wavy definition. Like if you compare it to humans, let's say whenever we think about cat, we have a certain activation pattern in our head that being projected to a 2D space, constrained by 2D boundaries, is let's imagine it looks something like this. So in initial concept space, we have cat, truck, car, dog, all are separated from each other because we know them as all distinct things. The model also, after fine tuning, knows them as distinct things. But if we do global fine tuning, like if we allow all the weights of the model or maximum of the weights of the model to change on seeing the new data points, then it leads to very bad scenarios of very high catastrophic forgetting. As you can see, concepts are getting mixed up. Trucks, dogs, cat, car. Like if I am trying to even teach about truck, the same cloth analogy. I lift the manifold a bit here, then all these other areas got stretched, and the fine, delicate connection between the text and the image tokens got disturbed. The solution for it, using low rank adapters. Here we introduce small number of parameters which are changed on the fine-tuned data from the gradient descent. But still we see some overlap between the same related structures, same related concepts like automobiles, trucks and cars start getting intermingled between each other. Now comes DSCA, our method. In this method, suppose we want to teach the model a very specific type of truck, then it doesn't mingle with the other concept spaces of cat, car, and dog. Let's say it just learns a single rotation or whatever small changes we want to do with the truck's concept space. It learns that that controlled changes only. So these are like very high level explanation. We'll go into the details. Like this is a way to wrap our mind around the problem. Obviously, it's a low dimensional representation. In our brain, we don't think in terms of points. There is no certain point in our brain which thinks about certain characteristic of a cat. But these are all you can imagine as activation maps in our neurons, in the neurons of the model, with the internal layers, and they are projected into a 2D space for visualization. So how like DSCA prevents this intermingling of concepts? So first comes the DSAMPs. DSAMP, this psi k HF. So in VLMs across different layers, we have three levels of representation. Not three levels, three different modalities of representation. The text goes through the text encoders and internal text representations are generated. The image goes through the vision encoder and the internal image representations of image tokens are generated. This HF are the fused tokens. So fused tokens are generated once once the semantic meaning of both text and images are combined into one representation. So essentially, our intuition was, what if uh, for a single for let's say for a single type of task which we want to the model to learn, we call it a edit. We have n number of examples in that, and we pass it through the model. During inference, we will have different values of this internal fused representations. Then what we'll do, we will form clusters of those fused representations. Suppose if I want to teach the model, this is a Cybertruck, then there will be the fused representations. One concept will be centered around the truck. Some concepts will be centered around car because it looks like a car. From visual stream, it is looking like a car. And obviously, there will be there is a composition between these two concepts. So inherently, our idea was knowledge is compositional. So this dsam parameter, this psi k, gives us a edit in the activation in the fused internal representation of the model. We generally took it at the center, at the middle of the attention layers. So this HF is coming from up from downstream. We have given the image and the text. After mixing their encodings, we get this fused representation. We say if we apply psi k, this k parameter is very important. K refers to the specific concept cluster to which we are referring. So this psi k does what? It gives us delta h. It gives us a small delta which needed. It's as you can see the gated residual, which gives us a value which should be added to HF to align it to so that in the end it predicts the correct thing. Like all these things are trained, but from a high level, this psi k for HF for each concept it gives us a delta HF, a small residual which should be added to the fuse representation right at that point. This is a part of the representation learning, so that in the downstream task, the model's outcome is driven by this internal fuse tokens, these edited fuse tokens. So now let's understand a bit into the architecture. This RK, what is this RK is semantic subspace. Remember I told you about concepts. So these concept spaces are essentially collection of different HFs. So if we project those HFs into a low dimension, because these HFs are high dimensional, maybe 1024, maybe 3048, they can be very high dimensional. So, and we know the curse of dimensionality. If we are dealing with very high dimensional spaces, then the number of parameters required to learn a representation in that space is also high. So we derive RK. In RK, the rows are essentially the principal components, are the top R principal components of all this collection of HF in one concept. So one concept refers to the subscript K. RK is the semantic subspace of that concept. So RKHF projects the internal fused representation into that subspace in which we are trying to do edit. Now WKHF plus BK, it performs a linear transformation on the same HF, and we do this. We find this difference. This WK and BK are trainable parameters, and mind RK is not a trainable parameter. It's just derived as a continual PCA on the clusters of HF which you are forming, which you are calling them as one concept. And back then again, we are moving them back by RK transpose, we are moving them back again to the original HF space, because the model should have HF in the dimension in which it originally produced, right? So to give a delta, and the delta HF should be should have same dimensions as HF. And then finally, we have this getting parameter. This getting parameter modulates each dimension of the edit which you are proposing. Let's say we are proposing an edit in the concept of dogs, but this concept of dogs has, let's say, 1024 dimensions internally, representing the uh, color of the fur, one representing the shape of the tail, a lot of things. But when we are trying to teach a model about a particular type of dog, it is not necessary that all the aspects of dog need to be changed and need to be added to the initial representation what the frozen model produced. So that this lambda HF, this gamma HF is a gating parameter. It also has internal learning weights. But what it does is it basically modulates each dimension in the edit which you are proposing, so that the edit is controlled. So now we get this shy k. So let's say we are trying to teach a model a very new thing. It is very unfamiliar that all the previous concepts the model has learned, all are activated at once. There should be some fixed number of like k equal to 1, 7, 8, 9. So this psi k is for that concept which are selected, and how that selection mechanism happens. You look into the if you look into our paper, there is one level of coarse visual filtering, then text-based filtering. So that there are two levels of filtering. You can look into that. So the meat of the thing is we propose different for one edit. We propose how we propose different residual edits across the internal fused representations, which is modulated by some getting parameter lambda k. And like if you look into this, this delta HF is a summation of this WK is a weighing parameter. Again, each concept as a whole should not be, even after modulating, each concept as a whole should not be represented given equal weight. So that's why we introduce one more sparsity parameter, WK, which which we try to invoke as much less concepts as possible during an edit. This is to exactly to have more and more reliability, and to have the model learn what the new things which we are giving. Or else there will be an averaging effect. If every concept is given, every chosen concept in the K is given equal weightage, then there will be an averaging effect. Yeah, so this coarse visual filtering followed by fused routing. This is the hierarchical routing part, which we have not presented in poster. So what are the training objectives? What are the tasks on which we train the model? The first task is causal LM. So this is a standard cross entropy loss. So if IE, TE, these are the edit samples. If we have an example where TE is the text of the edit sample and IE is the image of the edit sample, then finally, what logics the model is producing, it should be similar. This target logic should be similar to what we expect the model to say as the output in our data set, in our edit database. So this is a standard cross entropy causal language modeling loss. So coming up to the second term, uh, here this is cross modal alignment loss. So what we are trying to do is the difference, the S dash V is the edited visual internal visual representation. But one thing may arise in your mind, we are just editing the fused representations. Then somewhere this visual edit is also coming. So what we essentially do is we add whatever edit we propose for, because HV and HF, the visual internal representation and the fused internal representations are in the same dimensions. So whatever edit we proposed in the fused representation, we simply add that to the visual representation as well to get this H dash V E means edit out of the edit data set. Then we find its similarity with the text, unedited text data set. So why do we do it? We do it so that the model doesn't drift. The initial problem which I mentioned, these models have learned a very delicate balance between the text tokens and the vision tokens. So we are ensuring our edits, whichever we are proposing, are not diverting. This is a standard cosine similarity distance only between cosine distance only between these two, HT and H dash V. So our model is not significantly deviating from its text counterpart, even after edits. Since it is modeled as a loss, uh, independently, this term higher the better, but we do it 1 minus because the loss in the end should, the lower the loss is, it is better. And then we have the contrastive distillation loss. This you can imagine this like if we are trying to lift the cloth from one point, contrastive distillation puts nails at other points so that others are not getting disturbed. So how we exactly achieve it? So this is also a cosine similarity, but we have converted into a softmax using a temperature parameter. The H dash F O means out of distribution, the things on which we are not editing. And it's suppose we pass an example of out of training set data to our model. Then in that case, also there are these DSAM parameters are also there. So the some edit will also will be proposed. So we will get one H dash F. So that H dash F should be as similar as possible the frozen HF. Frozen means we have frozen the same model without using the DSAM parameter. So exactly at that layer, after editing for out of distribution examples, this the internal fused representation after edit should remain as close as to the frozen internal representation. So and why the minus? Because as I have said, loss it should as be as less as possible. This log term should be as more as possible. But since it is a loss, we have put a minus in front of it. And this gate sparsity loss, which I was telling, like even if after initial two stages of filtering, for each example, we are filtering only some case, some concept spaces. But inside that also, we need not to activate all of them. So for that, we apply a sparsity loss on weight for each K. And you can see it is mean, it's an absolute loss because we want because this type of loss enforces as much as possible. This WK should be zero and this should be sparse. This WK matrix, if we plot, it should be sparse across the concepts. And this is the training. So this explains the loss signals, the four losses which we use, and in the initial tries, the lambda which we use was one, like the weightage of each loss in the final loss calculation. But in our ablation, in our supplementary material, we have written what exact number which we use to weight these losses. And now DSA training loop is simple. Sample batches from DE and DO. So DE is edit sample and DO is out of distribution, which you have, which will essentially act as a replay for the model. Extract and fuse features. So yeah, HF after the uh, after the fusion block, we get out this HFs from the computational graph, which the model draws during the inference only. It's a training free method. We are just doing inference during we are just doing the edits during the inference only. Cluster and root. Yeah, as I said, update concept prototypes with edit samples, find candidate concepts. So concept prototypes means the centroid, all these clusters of which we say as these are one concepts which consist of all these HF have one centroid that we call as a prototype. So if we see this centroid needs to be updated based on the data which we have pushed into the model during inference, then that will be updated according to one threshold. The details are in the paper. Then we find candidate concepts with the two stages, two stage concept selection. Then we compute these WK weights, which is this concept level sparsity weights. Then we do the intervention. Intervention, we calculate for each K, for each selected concept, we calculate the residual which should be added to the HF by via this psi-K, which I explained here. The DSAM modules give us this psi-K values, this intervention parameter, and these are also weighted by gamma K. Like each individual dimension is also weighted by one another matrix, so that we don't add all of them to the original HF. Then we compute these losses. We update the DSAM parameters. Then we periodically refine this RK. As the concept distribution changes, their PCA, their principal component accesses, top R will also change. So once we see we have set threshold for that, once we see that our prototype have moved a lot beyond a certain threshold, then we'll have to refine this RK. These are not, to be very clear, RK are not trainable parameters. These are only the principal components of the concept spaces which we have built so far. So this explains like how we do the edit and all in the mid layers by extracting the representations in mid layer, adding the residuals, and then allowing that residual mixed edits to propagate in the further layers. This drives the LLM generation towards the tokens which we want actually. Then let's look at the matrices. How will prove uh, how will prove that our process works? So the first is it is a single edit success. We for a single particular type of edit, we want to teach a model. Let's say the concept of Cybertruck. So we have 10, 20 examples of Cybertruck images and their description, and we want to teach the model about that only. In that case, this EVQA, EIC are two different benchmarking data sets, which you can say. And these matrices are very important. This is reliability. Reliability means how good this edit was. Like after this, after we train our DSAM parameters on this particular task, which represent Tesla Cybertruck. After that, if we ask a question about Cybertruck, how good actually it responds. So this number uh, uh, reports that as you can see, we are beating most of them, most of the previous this to now are the state of the art, previous state of dual edit or the state of the art for it. We are beating it by some percentage. Then TGen, this is text generalization. If after training fine tuning the DSAM parameters for a particular type of knowledge editing, if you reframe the text, ask the same question in different text formats, which we can do, right? So in that case, how good is the generalization? Like how good is the model able to adhere to understand? Yeah, they're asking about the same thing only, but in a different language sequence. So that also we achieve state of the art. Vision is vision generalization. In vision generalization, we in different angles we are showing Tesla Cybertruck in occluded formats. Whether in those scenarios also, whether the model is able to know whether it's a recall that yes, this is the Cybertruck on which it has been fine tuned on. So in this also we report the highest value. And the TLOC, MLOC, these are the localization things. Localization things means these are related to unrelated concepts. If after rating on a proper concept, after rating on a proper knowledge, we'll ask the model random unrelated things. And if the model still remembers the past knowledge it had, this localization matrices show that. TLOC means text localization will ask random other text based questions, and MLOC is multimodal modality localization. Will show the model other images. Let's say we fine tuned out car, and we'll show it satellite images and ask it whether that knowledge that during pre-training which it had about satellite images, whether it remembers or not. That refers to MLOC. And average is averaging of all these numbers. So as you can see, we are beating the state of the art by a very good margin and in across all these metrics. Now comes the lifelong editing result, which is like yeah, and I forgot to say we did all this experiment on Lava 1.5 7 billion parameter module. Lifelong edit equal 1,000 edits. So what we do is we do sequential edits. First, let's teach the model one task. Then let's just teach the model another task. Like this, we'll teach the model 1,000 sequentially. We'll teach the model 1,000 different things. At the end of that, we will measure how good the model is on the very first task. Reliability, which we taught. The very first task, which we taught the model. As you can see, all these metrics are the same from the above table only. So here also, even after 1,000 sequential edits, we achieve state-of-the-art performance. Like it preserves all the previous knowledge. It is not like that our DSCA parameters can't handle multiple edits. If you increase the number of edits, then also the parameter space is enough to withhold those knowledge so that we can steer the generation right during the inference time to give answers about those questions. Now let's move on to the coin benchmark. Coin benchmark is one of the best benchmarks for measuring how good we are doing the knowledge editing across different tasks. As far as I remember, coin benchmark has 8 different tasks. Task can be visual question answering, scientific question answering like scientific diagram understanding, OCRs, text documents, then image classifications. So like this, we have 8 tasks in Coin. And what essentially what it does is we'll train one after the other on all the tasks and report all these matrices: SCC, BWT, FWT, and AT. So SCC is average accuracy. Means after we have trained across sequentially trained our fine-tuned our model across all these 8 tasks, what is the average accuracy on this each of the on each of the individual tasks? In this number also you can see we are beating Google's Palm. It was the state-of-the-art model in knowledge editing before DSCA, but we have beat them by a fairly good amount. Then BWT is backward transfer. Backward transfer means once, let's say, task A, B, C have already been trained, and now we trained it on task D. But now we are asking questions to the model about task A. We are asking question to the model about task B. So all the previously learned tasks, we are asking the model questions about them, and it essentially measures how good the model is preserving its knowledge, how good the fine-tuning technique is giving the model the ability to preserve the knowledge. And the more negative it is, the more knowledge bleed out it is happening. So as you can see, Google Spam had minus 19.45, and ours we cut it by almost half by reducing down it to minus 9. So this number shows our model, our fine-tuning technique prevents the model from leaking out its past knowledge. Then FWT as BWT, it is forward transfer, but its definition is a bit different. In forward transfer, let's say we have trained our model on task A and B, and then we trained the model on task C, and we asked what is the accuracy now. Versus we directly trained our model in task C without training it on task A and B. So what it essentially says is how good our fine-tuning technique is helping our model to generalize the pastly learned tasks into the next upcoming task. So in this also, we are reporting almost the similar numbers as Google's Palm. Then finally, AT. AT is the plasticity matrix. Plasticity matrix. Plasticity means how good the model is during after fine tuning. The model is able to adapt this out of distribution data which it had never seen. That's why you're fine tuning it on it, right? So how good it is able to adapt to that data. How good accuracy it is showing on that particular data after fine tuning. So this is the plasticity matrix. In this also, we are reporting number which is fairly comparable to the previous state of the art, which was MOE LoRa, but it was failing in all other scenarios. But ours is preserving the past knowledge, giving good forward transfer scores, and as well as giving us good plasticity. So this was my walkthrough around the state of the art results which we got out of the DSCA knowledge editing paradigm. I hope some of the viewers will work on this, will take this work forward. This is a part of representation learning, like doing editing, right? When the LLM is going through its computational graph, it is a training-free method as well. We trained it fairly easily on only one GPU. So thanks for joining. See you at CVPR. Thanks.